So I'm going to speak about mixed multiplicities of graded algebras and mixed volumes of lattice polytopes. Here is the brief outline. I'll first mention historical background and recall the concept of Newton polytope, Hilbert function, and Hilbert polynomial of a graded algebra. Then I will explain how degree of a toric variety can be computed in terms of certain volume of a polytope. I will then discuss the Brun-Minkowski theorem for mixed volume of a set of polytopes. I've lost the slides. Slides are lost. Hmm?
The sharing is wrong.
Okay. It says you are sharing the screen.
In the screen.
Yeah. All right. Okay. So the purpose of introducing these concepts is to discuss a theorem of Bernstein about number of zeros of Laurent polynomials in the complex torus in terms of mixed volumes of their Newton polytopes, and we will see that the classical theorem of Bézout is implied by this theorem of Bernstein. I will then move on to show the connection of mixed multiplicities with the Hilbert functions of multigraded algebras and derive a formula for mixed volumes of lattice polytopes in terms of mixed multiplicity of monomial ideals. And this formula will lead to a program which has been implemented in the software called Macaulay 2. So let me begin with the brief historical background. So it really begins with fundamental theorem of algebra due to Gauss, proved in 1799 in his thesis, which says that every degree n complex polynomial has n complex roots if counted properly with multiplicity. And in the same year, this theorem was generalized by Bézout, and he for bivariate polynomials with complex coefficients. Suppose you have two polynomials which have finitely many complex solutions, then the number of solutions is at most the product of their degrees. Bézout's theorem implies the fundamental theorem of algebra because you just look at the curve y equal to fx and count the intersections with the x-axis. The degree of the curve y equal to fx is degree of f, and the degree of the curve defined by x-axis is 1. So Bézout's theorem implies the fundamental theorem of algebra very easily. But a far-reaching generalization of Bézout's theorem using methods of convex geometry was obtained by several Russian mathematicians in 1970s. And this method can be traced back to Isaac Newton, who actually proved Bézout's theorem, and it is actually lemma 28 in volume 1 of Principia. This was published 90 years before Bézout's theorem came out. So it again proves that name of a theorem doesn't really mean that that person proved that theorem. So Newton used a polytope to prove Bézout's theorem, and this polytope is now known as Newton polytope, and it is a geometric representation of a multivariate Laurent polynomial. This polytope is now extensively used in theory of singularities of algebraic varieties, and it has given very interesting interpretations of invariants of singularities. So let me introduce Newton polytope to a Laurent polynomial. First of all, convex cell of finitely many points in n-dimensional Euclidean space is called a convex polytope. And if these points are lattice points, that is points where the coordinates are integers, then it is called a lattice polytope. So take a multivariate Laurent polynomial, write it as a sum of monomials, and compact notation for monomial is x to the u. Yeah, so x to the u is x1 to the u1, x2 to the u2, etc. So take these monomials which are occurring in this multivariate Laurent polynomial and take the exponent vectors. So there are finitely many exponent vectors which are coming from these monomials, and take the convex hull of these finitely many lattice points. That is called the Newton polytope of this Laurent polynomial. So it completely disregards the coefficients. It only looks at which monomial are occurring. And for each monomial, I have a lattice point, and there are finitely many lattice points. Take the convex hull. That is the Newton polytope. So, for example, if I have a bivariate polynomial, and I display the monomials which are occurring in this polynomial, then I have n lattice points in the plane. Okay, so these exponent vectors are coming from the monomials. I take the convex hull of these n points. That is called a Newton polygon. For example, if I take g equal to a1 plus a2x plus a3xy plus a4y, this is a polynomial of degree 2, and h, another a polynomial of degree 3, and these coefficients bi's and ai's are non-zero, then the Newton polygon of g is this square, and Newton polygon of h is a triangle, and the solid triangle. It's a convex set. So these are the Newton polygons of these polynomials. So there is no attention paid to the coefficients, and we get nice convex polytopes, which are representations of these polynomials. Now we will need the notion of volume of a polytope. This is the Euclidean volume. So a polytope in Rn, then its n-dimensional volume is defined to be 0 if the dimension of the polytope is less than n. Otherwise, it is defined to be the n-fold integral carried out over this polytope. Polytope is a closed bounded set, it's a compact set, and you take this n-fold integral to calculate the Euclidean volume. So volume, if the dimension of P is less than the dimension of the ambient space in which P is embedded, then the volume is 0. Otherwise, it is this finite real number. So, for example,
dimension of a polytope is defined as a hyperplane in which it lies.
No. So it's a topological space in the Euclidean space, and the usual notion of dimension. Yeah. So one can do it linear algebra way also. So a polytope, this is a convex set. So I have between any 2 points, there is a line segment. It completely lies in P. So what you do is extend this line segment and make it a full line, infinite line. And so there is this set in the Euclidean space which is obtained as affine hull of P, and any affine set has a dimension. It's a translate of a subspace of Rn, and dimension of that subspace is the dimension of the polytope.
So the volume is exactly the Lebesgue measure, Professor Verma?
Yes, this is the Euclidean volume standard Lebesgue measure. Yeah. So I think I have lost this. Because of internet. Yeah. Just a minute. It says you are sharing your screen. I have to stop sharing first. Sorry. I can see in my iPad my screen, but I don't know what is going. I have to restart. Maybe.
You could put the Zoom in that and start.
Yeah, just a minute. We need a technical expert. It says share invite. The share screen. Start broadcast. Yeah. Screen broadcast. Let me stop this. I will go to this. I will share the screen from here. To open the file. No, now we'll share the screen. Where?
He's coming. Yeah.
Maybe full screen. Okay. All right. So sorry about the interruption. So I was telling the volume of polytope and dimension of a polytope. As I said, take the smallest affine set which contains P, and that affine subspace is a translate of a subspace of Rn, and dimension of that linear space is called the dimension of the polytope. It coincides with the topological dimension. So if the dimension of P is equal to n, then the volume is this multiple integral. For example, if I take the polytope PL, which consists of real points A1, A2, AN, where AIs are non-negative, and the sum is at most L, then the volume of this simplex is Ln over n factorial. This is a good exercise in change of coordinates. You just define the following transformation: phi x1, x2, xn is 1 minus x1, x1, 1 minus x2, etc. And this change of coordinates is going to map unit cube to P1. And by change of variable formula, the volume of P1 is the multiple integral over unit cube, and it is 1 over n factorial. You make one more change of variables, xi going to Lxi, and then the volume of PL is Ln over n factorial. Pardon? L is up to which number it goes in each direction. Yeah, this is the simplex. Yeah. All right. So I want to now recall the Hilbert-Serre theorem. to connect volume with degree of a projective variety. So this is done through Hilbert-Serre theorem for graded algebras. So take K to be a field, and n-graded algebra is a commutative ring containing a sequence of vector spaces over a field K, so that the algebra is a direct sum, and Ri times Rj is contained in the I plus j graded component. So it's a graded algebra graded by the semigroup n. The elements of Ri are called homogeneous of degree I. Then the ring R is a Noetherian ring if and only if there are finitely many homogeneous elements of certain degrees, so that R is a affine algebra over this field generated by these homogeneous elements. It is called standard if the degrees of these polynomials are all 1. Okay, so once we have standard graded algebra, then one can derive many invariants of the ring R through Hilbert function. So first recall dimension. The Krul dimension of R is the maximum number of algebraically independent elements over K inside R. That's the Krul dimension. The Hilbert function keeps track of the dimensions of the graded pieces. Okay, so HRN is the Hilbert function of R, and it is the dimension of nth graded component. And if that dimension of R is d plus 1, then the multiplicity of R is the positive integer, which is limit of d factorial HRN over n to the d. Okay, so that's called the multiplicity of R in algebra. And if R happens to be the homogeneous coordinate ring of a projective variety, then it is called the degree of the projective variety. Hilbert-Serre theorem says that there is a polynomial with rational coefficients, so that this polynomial gives the dimension of the nth graded component for large n. So up to some n, we can't get the Hilbert function from the polynomial, but beyond certain n, the values of the Hilbert function are extracted from this polynomial by substituting x equal to n. And moreover, the Krul dimension is 1 more than the degree of this polynomial. So this Hilbert polynomial hides lots of invariants of the projective variety whose coordinate ring is R. So the dimension of the projective variety is precisely the degree of the Hilbert polynomial, and the leading coefficient, normalized leading coefficient, is the degree of the projective variety. Okay. Yeah. So for example, if you take polynomial ring in d plus 1 variables, then the dimension of Rn is this binomial n plus d choose d for all n bigger than or equal to 0. So it becomes a polynomial right from the beginning. And if you see, the leading coefficient is 1, and that indicates for the affine space, the degree of the affine space is 1. Okay. How does volume of a polytope enters this area? So take a polynomial ring in n variables and take a finite set of monomials in A. Okay. Finite set of monomials of any degree you want, but it should be a finite set of monomials. Then take the subalgebra generated by these finitely many monomials, and this is called affine semigroup ring. Okay. So finitely many monomials of any degree, they will define a Noetherian ring. It's a graded algebra. And so this affine semigroup ring interacts with many convex geometry as well as algebra. So from each monomial, I extract a exponent vector u1, u2, un that gives rise to a lattice point in the n-dimensional Euclidean space. I have finitely many monomials. Each monomial will give rise to a lattice point in Rn. Take the convex hull of those lattice points. So that is the polytope we associated with this affine semigroup ring. Okay. But on the other hand, we can also associate a group. So take a subgroup of the free group Zn, which is generated by the column vectors, which are these lattice points coming from monomials. So that's a finitely generated subgroup of Zn, and the dimension of this semigroup ring, the Krul dimension, is the rank of this subgroup of Zn. Okay. Then if the exponent vectors of these monomials, they are contained in affine hyperplane, then the semigroup ring is a standard graded K algebra. So take say monomials of degree D. So all these monomials of degree D, they are now considered degree 1, and then the semigroup ring becomes a standard graded algebra. So when you have standard graded algebra by Hilbert-Serre theorem, the multiplicity makes sense because the Hilbert function becomes a polynomial for large n. I can express the multiplicity of the semigroup ring in terms of certain volume of a polytope. Okay. So how to get the polytope? Well, let Qm be the convex hull in Rn of points in the exponent vectors. So I start with finitely many monomials, and these finitely many monomials, we plot them in the n-dimensional space, take the convex hull, that is the polytope that I'm going to associate with this semigroup ring or these finitely many monomials. Okay. Take this polytope, then the dimension of this polytope is 1 less than the true dimension of the semigroup ring. So dimension of the semigroup ring is, of course, the maximum number of algebraically independent monomials among the monomials that we choose in the beginning. But its dimension is 1 more than the polytope that you get. So the algebraic invariant, which is the true dimension, is coming from the dimension of the polytope. It is 1 more than the dimension of the polytope. Okay, so I'll show in an example. Suppose R is the dimension of the polytope Qn. M is my fixed set of monomials. Take the polytope, which is convex hull of the exponent vectors of these monomials. For R is the dimension. And take a basis of the subgroup, which is generated by the exponent vectors in size Zn. So on one end, I have the polytope. On another end, I have the subgroup. Okay, and this take a basis of that subgroup. So that is a subset of M, and with respect to that subset of M will also give rise to a convex polytope. And suppose the R is the dimension of this convex polytope. Okay, then the multiplicity of the semigroup ring is an integer, and that integer is quotient of the R dimensional volume of this polytope Qm over the R dimensional polytope. I mean R dimensional volume of the polytope Qe, where E is the basis of this finitely generated subgroup of Zn. Okay, so this is on the right hand side. I may have some irrational numbers, but their quotient is always a positive integer. Okay, so that is the geometric interpretation of the multiplicity or Km. Km, if Km is an integrally closed ring in its quotient field, then this Km is a homogeneous coordinate of a toric variety, and this degree of this toric variety is the quotient of volumes of these polytopes. For example, if I take these three monomials, x square, xy, and y square, then I plot these exponent vectors. The exponent vectors are 3 points in the plane. The points 2, 0, 1, 1, and 0, 2. They form a line segment. And the Hilbert function of this semigroup ring is, one can calculate easily, it is 2n plus 1 for all n. And so the Hilbert polynomial is 2n plus 1. The dimension of this ring is 1 more than the degree of the Hilbert polynomial. Degree of the Hilbert polynomial is 1. So the full dimension is 2. And you can see that x square and y square are algebraically independent monomials. So that dimension is 2. And the multiplicity, I can use this formula. For the multiplicity and get this polytope Qm. Qm is the polytope which is generated by, which is the convex hull of these 3 points in the plane. That's a convex, that's a line segment. It is one dimensional. I find the length of this line segment, divide by the length of the line segment, which is corresponding to the basis. And you can check that it is actually 2 root 2 over root 2, and it is equal to 2. And this is a quadric surface, x square, xy, y square. It is a quotient of polynomial ring in 3 variables. And this represents the affine coordinate ring of a quadric surface in 3-dimensional affine space. And that degree of quadric surface is 2. So that's how these numbers are coming up here. All right. So now I go to mixed volumes of polytopes. These are classically studied by Minkowski. And these mixed volumes have lots of applications in applied mathematics also. For example, if you read the book of Bernstein-Fels on polynomial equations, he points out that in game theory, there is a notion called Nash equilibrium. And to compute the Nash equilibrium, one has to calculate mixed volumes of polytopes. So to get mixed volumes of polytopes, they define mixed volumes, and one needs very efficient algorithms to calculate these quantities. So what is a mixed volume? Mixed volume of certain number of polytopes is a non-negative real number. And this is defined to be an alternating sum. So so we have these certain number of polytopes, and you add up these polytopes. This is called Minkowski's sum. So if I have two polytopes P and Q, I simply take the sum of vectors which are in P and Q, and that happens to be a convex polytope. And this is called the Minkowski's sum, and take the volume of this polytope, but multiply this by -1 to the power n minus cardinality of j, where I'm taking these pi's, where I is varying from j, and j is varying over all subsets of 1 up to n. So it is an alternating sum of real numbers. It's not clear whether it is non-negative, but one proves in convex geometry, classical convex geometry, that it is a non-negative real number.
So sum of polytopes is in the vector space, right?
Yeah, it is. Yeah, this is being added in Rn. Pi's are
Okay,
added in Rn.
Right. Yeah.
Volume is a real number.
Right.
Fine, it can be 0. Yeah, it can be 0. But it is non-negative, always. That needs some proof. No, there are no assumptions. These are polytopes. These need not be lattice polytopes also. Any polytopes. In fact, any compact convex bodies, one can define mixed volume. Same definition. Okay. So take polytopes, finitely many polytopes, and suppose pi's are contained in qi's, and these pi's are also polytopes. Then the mixed volume of the polytope P1 up to PR is less than or equal to mixed volume of Q1 up to QR. So this is monotonic property. Okay, this is intuitively clear, but one needs a proof. Okay, then mixed volume is multilinear, just like determinants. Volume for special classes of polytopes is a multilinear. It is given by some determinants, and determinants are multilinear. Same property is true for mixed volume also. It is a multilinear function. It is invariant under translation because volume is invariant under translation. So the mixed volume is also invariant under translation. So each polytope can be translated by some fixed vector, and it will not affect the mixed volume. This is a classical theorem of Brun and Minkowski, proved in 1896 and 1887 independently. Suppose I take Q1 up to Qs, these are polytopes, and I take their Minkowski sum, and R is the dimension. When you take Minkowski's sum, the dimension can increase. If I take, say, one segment on x-axis and another line segment on y-axis, then the Minkowski's sum is a polygon. So the dimension is 2 in that case. So dimension can increase if you keep on adding these polytopes. So suppose R is the dimension of the Minkowski's sum of S polytopes, and let Q alpha be the multiset. It's a multiset which contains alpha I copies of the ith polytope, and the sum of alpha is equal to the dimension of the Minkowski sum. Now I take non-negative real numbers, lambda 1, lambda 2, lambda s. Okay, and now find the volume, R dimension volume of this real linear combination of Q1, Q2, Qs, and vary lambda i's over all non-negative real numbers. Okay, so that's a function. That's a multivariate function of lambda 1, lambda 2, lambda s. I'm keeping these qi's fixed, but varying lambda i's. Okay. Then this theorem of Minkowski and Brun says that this is a homogeneous polynomial in lambda 1, lambda 2, lambda s. And if you write this polynomial in this multinomial, as we display things in multinomial theorem, lambda 1 alpha 1, lambda 2 alpha 2, lambda s alpha s over alpha 1 factorial, alpha 2 factorial, alpha s factorial, and then the coefficients are the mixed volume of these multisets. Okay, so it's a real homogeneous polynomial. Its degree is the dimension of the Minkowski sum, and the coefficients are mixed volumes. So mixed volumes were defined using this alternating sum. But now you see the right and left hand side. Left hand side is a non-negative real number because it is r-dimensional volume. It's a non-negative real number, and this is valid for all the lambda i's. And now it's easy to see that these mixed volumes are non-negative real numbers. From this formula, it follows that these are non-negative real numbers. And many other properties can also be proved using this formula. Okay. So the question arises how to calculate these mixed volumes. Okay. All right. I have not read Minkowski's paper, but I have read the proofs in the standard textbooks. Yeah, this formula is obvious in one-dimensional space. Then you apply induction and use projections. Projection of a polytope is a polytope. So then find the relation between a polytope and its projection. The volumes are. I mean, Minkowski was using these things in number theory. Yeah, and if the volume exceeds certain number, it gives rise to a rational point. Yeah. For example, he gave a very simple proof of Lagrange's four-square theorem using convex geometry, which is, just a few lines. Right. Yeah.
Professor Verma, is the correct statement perhaps a trivial one to say that a polytope has zero volume precisely when it has empty interior?
No, it depends on if you take line segment in two-dimensional plane, it's at zero volume by definition.
So the volume of the segment in the plane will be zero?
Yeah, its interior is zero in the plane.
So
that's right.
Two statements seem to be equivalent, right?
Yeah, I think so. If volume is if the interior, if there's no interior, its volume should be zero.
Right.
Yeah. Okay. So let me show you this calculation of mixed volume because I need it in the next result. Take the standard simplex PD, where the sum of the coordinates is less than or equal to d, and these are the coordinates are non-negative real numbers. And take n real numbers and take these di's are positive. Then the sum of these simplexes, this Minkowski sum of these simplexes is a simplex, namely lambda 1 d1, lambda n dn, because if x1 plus x2 plus xn is less than or equal to d, and then y1 plus y2 plus yn is less than or equal to e, their sum is less than or equal to d plus e. And therefore, this gives this formula that this sum of these polytopes is this simplex, where the arm length is lambda 1 d1 plus lambda n dn. So by the earlier formula, the volume of this polytope is nth power of this length divided by n factorial. And by use the multinomial theorem, I express this in this way. And so the mixed volume of these simplexes is the coefficient of lambda 1, lambda 2, lambda n by the Brun-Minkowski theorem, and this is the product of di's. Okay, so the dimensions of, the arm lengths of these simplexes is being multiplied here to get this mixed volume, and perhaps that is the reason why it is called mixed. All right, so now let me state the theorem of Bernstein, Khovansky, and Kushnirenko. It's an amazing generalization of fundamental theorem of algebra. This is in literature called the BKK bound, proved in 1975 in the Russian Journal of Functional Analysis. Okay. So Russians had many journals, of course, but this Journal of Functional Analysis is a very famous journal, but it publishes papers in all areas of mathematics. They have not changed the name of the journal. Yeah. So it has this theorem, the papers of these three mathematicians appeared in 1975. So here is the generalization. Take Laurent polynomials in n variables, having finitely many common roots in the complex torus. Okay. So that is the condition. Because I'm looking at Laurent polynomial, so I can only talk about zeros in the complex torus. Okay. So suppose they have finitely many common roots in the complex torus. Then the number of common roots in the complex torus is at most the mixed volume of their Newton polytopes. Okay. So on one hand, we have a algebraic quantity, a discrete quantity, namely the number of roots. So if the number of roots is finite, it is bounded above by the mixed volume. And if these if I take these FIs to be generic polynomials, that is, I'm allowed to vary the coefficients. Newton polytope doesn't depend on the coefficients that you take, but you can vary F1 up to Fn over any n Laurent polynomials, but keep the Newton polytope fixed. They should have same Newton polytopes. Then in generic cases, this upper bound is actually achieved. Okay, so that is the content of this theorem. And coefficients can be general. Yeah. So if the coefficients are general coefficients, that is varying over some open set, then this bound is always achieved. Yeah. But it can be very, very small. Yeah. Depends on how these Newton polytopes are there. Okay. So this bound is attained when the polynomials are generic with fixed Newton polytopes. Okay. So you can vary the polynomials, but not the polytopes. Yeah. So this is the proof of Bezout's theorem using this bound. So suppose FIs have finitely many common zeros in Cn. I'm not saying the torus. These are polynomials, so I can talk about zeros in Cn. And suppose the degrees are di's. Then the number of common zeros of FIs is at most the product of the degrees. Okay, this statement can be made very precise if you introduce intersection multiplicities. And with intersection multiplicities, if you attach intersection multiplicity with the common zeros, then it is a very precise statement. And you can find a proof in the book of Fulton on toric varieties. It is in the last section of the book that he proves this theorem. Actually, he proves the BKK bound, and the BKK bound he proves using Riemann-Roch theorem for toric varieties. Okay. But there are other proofs also. All right, but let us see how Bezout's theorem is a simple consequence of this BKK bound.
The number of polynomials
Is n.
is different from
No, number of polynomials is n, and we are looking at zeros in Cn. That is a restriction.
so that gives you the finiteness.
Yeah, they have that gives the finiteness. But it's a general theorem of Heisenberg and Evans that any algebraic set is defined by n equations, at most n equations. So there is no loss of generality. In Cn, any algebraic set is defined by at most n equations. Right. So the assumption is that they have finitely many common roots. There is no common components between various FIs. So I have finitely many common roots, then this number of roots is at most the product of the degrees if you count with the multiplicity. Okay. Yeah, it's bounded by this.
Like saying at least one row in the case of
No, I didn't understand.
just now you also told take generic coefficient, then the bound is attained.
Yes.
That part is important.
Yeah. For generic ones, the bound is it. But if you attach intersection multiplicity, which I'm not going into it, it's a precise statement. The sum of intersection multiplicity is precisely the product of the degrees, no matter what is the FIs are. Only condition is they have finitely many common zeros. Okay. So first of all, these are polynomials. They have finitely many common zeros. So by translation, I can assume that the zeros are in the complex torus. Because this bound is only for zeros in complex torus. It is not a bound for in Cn. Okay, one can give examples. It cannot be a bound in Cn for Laurent polynomials. So, but if you begin with polynomials and they have finitely many common zeros, by translation, I can bring them in C star. That doesn't change the Newton polytopes, because translation, the mixed volume is invariant of the translation. Okay. So then the mixed volume of the Newton polytopes of Fi's. Now F1 is a degree D polynomial. So it has monomials up to degree D, a few monomials up to degree D. Now if you take all monomials of degree at most D, they are contained in the standard simplex whose arm length is D. So this Newton polytope F1 is contained in the simplex PD1, and Newton polytope of F2 is contained in the simplex PD2, etc. But these are bigger simplexes than the Newton polytopes Fi's. So when I replace these Newton polytope Fi's with the PD1, PD2, PDN, the monotonicity of the mixed volume says that this mixed volume is less equal to the mixed volume of PD1, PD2, PDN. But that mixed volume is the product of the degrees. That is the proof. Okay. So it's one of the simplest proof, geometrically obvious what is going on. Okay. And we didn't pay any attention to the coefficients of the polynomials, but we still get the bound. Okay. Now this bound is not sharp, okay, for algebraically closed field of prime characteristic. In prime characteristic, you can have polynomial of degree P with only one root. Okay. And the Newton, the volume of the line segment, so if you take this polynomial xp plus b, the Newton polytope is a line segment of length p and volume is p, but there's only one here. So in characteristic p, things can fail what you expect. But in characteristic 0, we have this precise bound and it is obtained for generic polynomial. So fx can be made a generic polynomial. Okay. You put one more coefficient in front of xp, fx can be made a generic polynomial. It is going to have one root. Okay. But Newton polytope has volume p, and therefore this is not a theorem in characteristic p. It's a characteristic 0 theorem. All right. How much time I have? It's over. Okay. Fine. So I'll stop here and take questions. No. I mean, you can triangulate a polytope by simplexes. But their Minkowski sum can be a polygon. Yeah, if you treat two lines are in independent directions. Yeah, then its volume is 0 in R. No.
My understanding polytope is this now L simplex. Then the problem is
No. Volumes can be they can be line segment or polygons or polyhedra in dimension p. Even then, the theorem is true. Theorem is true. But it depends on this dimension of the Minkowski sum of those polytopes. That can be bigger than the dimension of individual polytopes.
so volume and sum you are taking. Can it be negative?
No.
That is true.
Yeah. Mixed volume is a non-negative real. It follows from the Brun-Minkowski formula, because the left-hand side is a non-negative real number, and then the right-hand side, the mixed volumes occur as coefficients. But this formula is valid for all the lambda i's, and therefore those coefficients are also non-negative. I don't know. One of the objectives of this work is to calculate the volume and mixed volume of polytopes. So I didn't have time to go to the mixed volumes, but mixed volumes, just like volume of a polytope, came out as the leading coefficient of Hilbert polynomial of a semigroup ring. The mixed volume is also obtained in similar way. Yeah, and then one gets a formula. One gets a formula, and one can program that formula. No, RM. Yes.
Then, but only you need the usual
Euclidean volume. Yes.
But that turns out to be the limit for
Yes. Yeah. So same thing can be done for mixed volumes also, and so one gets a finitely generated algebra over a field, and we need to calculate its Hilbert polynomial, and that can be done through various software packages. And we have implemented this program, and it is giving the speed of this program is better than what is available using the classical methods of computing volumes. It's coming out in the next release of Macaulay 2.
So how do you prove that the volume
So that's in the last few slides. Right.
Professor Verma, can I just ask one simple?
I must learn hyperbolic space.
I am interested in the opposite question. I want to single one.
So in the Jacobian problem, we have two polynomials and so if it is onto map, do the FIs have finitely many common roots? Suppose you map.
Not in general.
Not in general.
You have these conditions, Jacobian conditions, not very constant. When you want single solution, global situation, local situation. Yeah. So it's opposite. Here you are giving also if you are assumed that we have finite, right? No common. Even that is no common problem. Two elements.
Yeah.
No, even in two elements.
I'll send you the paper.
Even in that. So, but whenever there are polynomials, my ears. So I hear.
Yeah. No, my question is in the Jacobian problem, you are sending x to a polynomial and y to another polynomial, and suppose the Jacobian is non-zero constant. Do these polynomials have finitely many common roots? Yeah. So they can have finitely many common roots.
That's true. Provided you have assumed Jacobian.
Yeah, assume Jacobian condition. Then they have finitely many common roots. What you want to prove is that there is only one common root. So we can try to calculate their mixed volume of these two polytopes.
Common thing is Newton's polynomial. Lot of work was done by Hilbert. Still finished.
Yeah.
Still there. He still says that there are a lot of new things. Those are his masters.
Yeah, the work on Newton polytope is never ending. Every year there are papers on Newton polytope, and the recent investigations are on what are called Newton-Okun curve bodies. So they have become very useful in singularity theory.
Slightly aside from the main theme of your talk, Professor Verma, what about the extreme points of
There
the
is some-
Minkowski sum of polytopes in terms of the extreme points of the individual polytopes?
Let's talk one more topic.